Thank you very much, everybody, for coming back and joining the stream. And now I'd like to welcome Andrew Hanson, MBE. He is Senior Scientist at the National Physical Laboratory, but also Outreach Manager. So he goes around the country explaining physics and physics concepts to a wide range of audiences. So we're really pleased that he's able to join us. As I said at the beginning, unfortunately, he's not here in person. That was the original plan, that he would join us actually here in Malvern at the theatres. But nevertheless, it's great to have you online. So Andrew, thank you ever so much. Andrew's going to be talking about colour and how we measure it.
Right, at the end of this talk, you may be convinced that the four colours shown here are identical. Colour is as crazy as that. And let's start off with this. Do you remember this? The dress. What colours are this dress? Some people say that they're one set of colours and some another set of colours. It was a social media frenzy, crazy thing going on a couple of years ago. Somebody broadcast this on social media and there was confusion about the colours and it hit all the headlines. It was fantastic. I was actually called to talk about it in the Telegraph. My mother was delighted. My father was disgusted. He said I should have been quoted in the Guardian. Never mind. I bought the dress. This is my daughter. Too small at the time to model it, but there we are standing next to it. And I illuminated it from two different sides with different brightness of lights. And they illustrated the problem really, really well, because you can see one side appears to be kind of white and gold, and the other side seems to be black and blue. But the original problem was that people viewing the image initially argued about which of these two sets of colors they saw. They could see the same in the same image. And so this gave colour scientists like myself an opportunity to flush out loads of arguments about why people see things differently. So I'm going to have to start, because I am NPL's outreach manager, by talking a little bit about what NPL is. We are the National Physical Laboratory, and I think when we were set up about 120 years ago, there was a misnomer, because I think the word physical should really have been measurement, because we are about physical measurement. It was about the physical sciences, which is why they used that word, but I think we really should have been called the National Measurement Laboratory, because that's the type of science that we do, measurement. And measurement is all around us, so it doesn't matter if you can't see the details in here. All you need to know is that making everything tick in a 21st century world relies on this underpinning facility that is good measurement, that industry knows exactly what a meter is, that trade knows what a kilogram is, etc. So radiotherapy, I wear glasses, and the measurements on my glasses enable me to see. So it's really, really important that measurement is done properly and internationally agreed if we are to internationally trade. This is the building that we were given in 1900 in the corner of Bushy Park near Hampton Court. And over time, we built lots and lots more buildings. This is the most recent one. It's actually white, but illuminated here, it looks glorious other colors. But inside here, there are 388 separate laboratory spaces, all very, very different, kitted out to do different types of science. This is one of the rooms. It's an anechoic chamber, a no echo room, and it's actually designed to do microwave measurements in. I don't know if you can see, there's above the gentleman's head, there's a kind of protruding horn, and that's sending out microwave radiation, which is then picked up by a sensor at the other end of the room at a very precisely known distance. And from this, we can work out either the power of the source or the response of the detector. And this is really useful if you're measuring how much radiation is coming out of mobile phones, or how sensitive your sky dish is, and other things. So really important measurements that underpin our nation. And way back, I'll talk about mostly about colour, because that's the world of work that I was involved in for many years. Way back in 1910, we were doing this sort of measurement. And here you've got three types of light bulb in order of age, perhaps. From the right-hand side, you have tungsten, piece of metal raised to a temperature of about 3,000 degrees. And most of the energy is lost as heat or infrared that we cannot see. A little bit of it comes out as light that we use to see by. But, if you want to talk about its efficiency, the proper word, efficacy, the amount of light coming out compared with the amount of electrical power going in is a bit rubbish, actually. But we then progressed to compact fluorescent tubes, which work a different way, and on the left-hand side, LEDs. And the two newer technologies, rather than wasting most of the energy as heat, I think about 5% of light comes from the electricity, if you like, that you put in. The others are more like 50 or 60% efficient, if you want to use that word. And the LEDs last longer. So that, I think, is our preferred technology these days. So measuring the efficacy of light sources was one of our earlier jobs. And nowadays, we're also worried about the color rendering, what things look like under these different types of light source. So you can't work where I do and not have some crazy stories. So let's plow through some of those right now for a bit of fun. So the top 5 oddest things that I know about. In at number 5, we've got measuring cauliflowers. Now, when you pick these things, you can't see whether they're ripe or not because they're covered in leaves. And if you pick them too early, they never ripen. And people are a bit picky about unripe food. And if you pick them too late, they just turn to mush. And people are very picky about horrible, gone-off food. So you've got to pick them at just the right moment. To do that, you really need X-ray vision. And to provide X-ray vision, we've created a kind of camera that uses terahertz imaging. Terahertz is a bit like microwave. It's a different part of the spectrum, the light spectrum. And it's the same technology that's used as full body scanners in airports. I don't know if you've ever stood in one of these things, but they can scan all of you and check for things. And when we're measuring cauliflowers, we're looking for the humidity content, which is an indication of its ripeness. So through this one application of technology, we have reduced waste considerably because people are picking stuff at the right time. So the yield of the crop has gone up, and your average Lincolnshire farmer now saves about £100,000 a year thanks to this this one innovation. In at number 4, do microwaves in phones fry your brains? It is the same stuff, 2.4-ish gigahertz. That is microwave. The thing is, a mobile phone that uses microwave chucks out radiation at a rate of about 700 to 1,000 watts, whereas your mobile phone, if it's working properly, should only be sending out about 1. So you could do some serious damage to someone by strapping 700 mobile phones to their head and turning them all simultaneously. I wouldn't advise it, but normally that's not the case. But there are regulations about how much radiation comes out of these things, and we were involved in measuring the absorption of this radiation using what we call phantom heads. So this model here absorbs radiation just the way the human brain does. In at number 3. Now, you can't claim anything in advertising unless you've backed it up with some scientific evidence. And so if you're going to say something like our razors shave closer than anybody else's, you have to have proved it somehow. And indeed, we were involved in that. We were sent several razor blade systems and a procedure. And we then measured how much of the stubble was left afterwards. It wasn't people's faces, it was stuff that looked like flock wallpaper. And we measured the length of the sort of stubble that was left afterwards. Very, very short indeed, so quite a complicated measurement to do, but we could do it. And that leads me to one of my favorite units. You can talk about funny units, which is the Beard second, which is how long stubble grows in a second, which is between 4 and 10 nanometers, which is a tiny, tiny amount. In at number 2, yes, I built a machine to measure how shiny cats are. Yeah. In at number 1, we measured the crispness of biscuits. And the way we did this was we actually listened to the sound they made when you broke them, the snapping sound, particularly in the ultrasonic region, the part of the audio spectrum that is above the threshold of human hearing. And that was an indicator of how crisp the biscuit was. Again, this was to investigate different types of wrapping and whether they kept biscuits crisper for longer by preventing humidity, water from getting in. So this is where we should have been today. Oh, well. Never mind. These are the theatres, and I thought it'd be good just to show an illustration here that shows where colour, because that's what I'm going to be talking about now, is used in our lives. So we use it for branding. There should have been adverts out there with my face on. explaining what was going on and, you know, whatever. And it's important when you have branding, whether you're printing your logo on a sign or on T-shirts, on headed notepaper or on the web page, that these colours that have been carefully chosen by psychologists, and they are reproduced faithfully throughout all these different media. So that's going to need some decent colour measurement, isn't it? Quality control. The building really ought to, if you start painting at one end, you want to make sure it's the same colour at the end. So you have quality control on paints. And imagine if you have to respray your car. That's also important, isn't it? And then finally, you've got legal and safety issues. And I put here double yellow lines. The council are obliged to go around and measure the reflectance of road markings. And if they drop below a certain level, they are obliged to repaint them. I mentioned about psychologists. This is a chart. I'm not quite sure whether I believe in any of this stuff, but there you go. There's a list of colors, different people who use them in their logos, and what people think these the way that the colors are used to manipulate emotion. And my eye was drawn to one of these colors in particular, that one there, because of course we always trust everything that we read in Twitter, don't we? Anyway, why do we need to measure and specify color? Well, we need to communicate colors for the branding thing and for safety. It's really important that traffic lights are the colors that we expect them to be, or they might be mistaken for something else. We also use them in monitoring. And here are some orange juices. Now, if one of those orange juices was redder, greener, yellow, blue, or whatever than the others, I bet you that's the one you won't buy because you think, oh, something a bit odd about that one. So, and also with paints, people want continuity in their product. And if you're communicating your brand internationally, because a lot of this stuff is made abroad, you need to use numbers for colors that everybody understands. You can't just describe your logo as being, well, it's a kind of nice blue. And the traffic lights, well, it's a sort of red. You've got to absolutely precisely describe them in what we call an absolute value. But if you're monitoring things, you're actually looking at changes and subtle differences. So communicating, measuring, and specifying colors are done in these different ways. We are human, and we have a particular human response to light. And if we take a white light source, I would have done this live, but we can't. And I can use a prism or something else to split it up, to kind of dissect white light. I would get a spectrum, a range of stuff like this. And as a physicist, I love to label things, to put numbers onto things. And so we talk about it in terms of the wavelength of light. Light is a wave, and the distance between successive crests is these numbers at the bottom. They're really, really small distances. And the waves in blue and violet light are much closer together than the ones in red light. So it kind of spreads out like this. But our eyes don't respond evenly to all these different types of light. And we are most responsive to light at the greeny yellow part of the spectrum. At the red end, actually, there's just not enough energy in the light to excite our eyes. And so we are kind of blind to infrared and everything beyond that. And we're kind of also blind to ultraviolet. Now, there is enough energy to stimulate the chemistry and biology in our eyes, but that would be dangerous. If that UV got to the back of our retina, we could do some serious harm. So there's a filter built into the eye to prevent that radiation, that light, from getting into our eyes. It's actually in the lens. So we are blind to UV. So does that make sense? There's a response curve to the human eye that's most in the green yellow part, but drops off at either side. This is for humans. Some animals, many animals, see different parts of the spectrum, and some can see ultraviolet and some can see infrared. So again, this is the demo that I would have done if I'd have been in the theatre. Never mind, I would have got my spectrum, I'd have projected it onto the wall, and I'd have had this thing, it's actually 2 bits of gaffer tape, one bit red and one bit green, and I would have gone for a walk through the spectrum, and it would look something like this. Now, with that object in the blue end of the spectrum, it doesn't reflect much light, so the red bit and the green bit both look a bit dull. But if I go for a walk with it into the yellow part of the spectrum, can you see the green is really bright now because it's reflecting lots of the light, but the red thing, well, it absorbs green light, it doesn't reflect much, and so it just still appears dark. If we go to the yellow part of the spectrum, something odd happens. Depending on where we are, the green might be brighter or the red might be brighter. And there's one point where they both look equal brightnesses. And from this, we can kind of work out that the sensation of yellow is actually a mixture of sensations of red and green together. And then if we take this thing to the red end of the spectrum, I guess you saw this coming, it's just going to look red, isn't it? Let's just take it out again. Those were the true colors. So you have objects that are colored, and you have light sources, and you have your eyes. And it's a combination of all of these that give the sensations of color. Now, if I wanted to measure stuff, because I come from a measurement laboratory, I would measure the spectral reflectance. So there's my spectrum. There are those numbers I spoke about earlier. And this is the percentage of light reflected as I went for a walk with this object through the spectrum. And I've got two lines here. The green line is how much light the green thing reflected, which, as you can see, is a peak in the greeny yellow part of the spectrum. Doesn't reflect much blue, doesn't reflect much red. And the other line that I've actually put as a bluey greeny color reflects a lot in the red part of the spectrum, but not much elsewhere. And you can see they're quite wiggly lines because measurements don't always give you results without noise. So there's a bit of jiggly variability in the results. But I suspect the curves are actually a lot smoother than these ones that are shown here. But from this, we can actually get some sort of idea about what these things look like, even under different types of light source. And as I mentioned, there are 3 stages of color production. There are loads and loads of different types of light source with different spectrums associated with them. And these things can go through, diffused by, reflected, transmitted, scattered by different types of object that change light in different ways. And then we also have different types of eyes, different people's eyes and different cameras and so on, measuring what's coming out of the system. Now, you can actually obviously be looking at the color of the light source directly, or indeed, as someone pointed out at one of these talks, you could close your eyes and you can still sometimes see color if you knock yourself on the back of the head. Don't do that just now. But the phosphenes, as they are called, are stimulated visual stuff, sort of pseudo-visual stuff in the human brain that's not actually as a result of light coming in through the optical sensors, but it's just some signals created within the brain. Okay, let's have some fun. So here's the moon. It's illuminating 2 boxes, and inside the boxes, I've got some sweet wrappers, and that's all very nice. Oh no, actually, I've not got sweet wrappers. Sorry, I've got some objects that are reflecting light. I can't actually see the objects reflecting light, but what comes out both appear to be yellow. So I've obviously got 2 yellow objects inside those boxes, okay? Now, I can do my measurement and I can actually find that this object only reflects light over this part of the spectrum. So that's the yellow part of the spectrum. So of course it's going to look yellow. Whereas this thing is reflecting light at lots more parts of the spectrum. But they all kind of sum up to give, again, the same sensation of yellow. So these 2 objects in there both appear identical in color. So you can have different spectral reflectance curves that appear to people as being identical in color. Okay, that's interesting. And then you get someone else to look at these 2 things and they see it differently because the senses, their eyes, their response of their eyes are different to yours. And I know people whose left eye and right eye actually see color differently. So for this person, they're seeing them as identical. For this person, they see them as being different. And they can have arguments. So one will say, oh, this is a perfect color match. And the other person says, no, it's not. It's not a color match at all. You're talking nonsense. In my experience, these little groups of 2 people are normally married to each other. We call this observer metamerism, and from their point of view, they are both talking the truth, but they will disagree because physically they are seeing different things. There's another type of metamerism, and it works like this. So here again, same setup, looking at moonlight reflected off 2 objects in a box, both appear to be yellow to one observer. But then we change the light source this time to something else. And because the spectrum entering the person's eye is a combination of the spectrum of the light source and also of the reflecting surfaces. They will actually appear different. So, and again, this can happen. You can buy two things that match perfectly in color under one type of light source, but not under another. Shops are really careful when they make their lighting to try and represent an average light source, so clothes shops, so that things that match in the store will match under a variety of different illuminants, but they don't always, and you can have fun with that. So here's your GCSE question. If I shine blue light onto a blue object, what color does it look? It looks blue because blue objects reflect blue light. Good. Here's the advanced question. What color is a red object when viewed under blue light? Who said purple? No, it's not purple. Who said blue? No, it's not blue, because the blue light is all being absorbed, isn't it? So nothing should reflect at all. So this individual should just see nothing. It should be black. That's what the marking scheme for this question says. I say, no, you're wrong. Two things could happen. One is that blue light could actually reflect off the surface because it might be glossy. It might be shiny. So you could sort of see a reflection of the light bulb in the red object off that top surface. So in this instance, you're seeing a bit of blue. And then also you could have this thing called fluorescence. Now that's called specular reflectance. You could also have this thing called fluorescence, where blue light, some of the energy is absorbed. I should have said that blue light contains more energy than red light. Some of the energy is absorbed and some of it is re-radiated as lower energy that we see as a different color. So I guess that you've seen fluorescent things, haven't you? The next time you get a fluorescent yellow thing, put it under some blue light and you will see it still looks yellow. So that is the process of fluorescence. Things looking different under different light sources. None of this was in the GCSE question. Right, so what makes color? I thought before I go into detail, I'll show you this. This is an invention that NPL made 20 years ago. It's an image, an electron microscope image, and we got some nickel phosphide, a metal, and we chucked some powerful acid onto it and rattled it around and created all these little micro crevices. I think it looks like Malteser. And these are designed to be about the same size as the wavelength of light, because light comes in, gets trapped inside there and cannot come out. And so this is NPL super black. This is the blackest black that has ever been made, or was at the time. Someone's made a blacker black since then, but never mind. And the idea is that light gets trapped in there and cannot come out. And we were using it as part of a camera because the energy is lost within the substance and raises the temperature through heat. We measure the temperature change, and then that's an indication of how much light is coming on. Now, the thing is that if I looked at this in the infrared, it would look really quite light coloured. It reflects lots of colour there. So this thing reflects differently at different parts of the spectrum. And that's the first clue as to how coloured objects are coloured. Oh, there's another super black. It really does look like that. It's weird. You cannot see the surface. You can't say whether that surface is far away from you or close to, because you can't see the surface. That's what the other super black looks like. This is the newer one, Vanta Black, made by the University of Surrey, which looks more, I think, more like carpet. They use nanofibers, and you can see there's been a bit of a break in the nanofibers here. But again, the fibers themselves are around, the pitch between them is similar to the size of waves of light, and so the light gets stuck in there. Right, so here's the book, The 15 Causes of Colour by Kurt Nasu. It's got 15 chapters, and each chapter more or less deals with a different way, a different material, a different property of materials that causes light not to be reflected by equal amounts at all wavelengths. I described this once as kinky spectra at a Royal College of Art meeting, and they all thought it was very funny. And so anything that doesn't reflect or give out light at equal amounts at all wavelengths appears colourful. And so these are the chemical reasons for colour. And as a physicist, I was a bit disappointed by that because I thought, oh, it's all to do with chemistry. And then here's the latter half of the book. And the last 4 chapters, that's what we'd call physics. But it doesn't matter. They're all very beautiful, and we've got lots of amazing things going on there that give us in the world sensations of colour. And here's an amazingly beautifully coloured thing. It's a dress from the 1870s. And the dye that was used to make that was a man-made or human-made dye. The first artificial dye. Previously, if you wanted purple, it had to be bits of crushed clam. But this guy here invented this particular pigment from coal tar. He was doing some experiments on coal tar. He was only 17, I think, when he did these first experiments. Go on, guess how old he is in that picture. How old do you think he is? He's aged 14. Is it the hair? I don't know. Anyway. And that is a selfie taken by him. He did the whole of the photography thing because that was what you did if you were a geek at that time. And his hand is like that. You can see his hand is a bit clenched because he's holding a mechanism for keeping the shutter open. So that's his self-portrait aged 14. He made millions out of this. And went on to make other colours as well. But highly fashionable chemical mix. A particular molecule that vibrates in a particular way and as a result absorbs light at some parts of the spectrum and not at others. And here's some chemistry going on inside here as leaves change. We're almost at that point of the time of the year when you see these. You can see all of these coloured leaves on one tree, which is at the same time. It's absolutely beautiful. And it gives you a clue about what's going on in the chemistry of the leaf. You've got chlorophyll, which absorbs solar radiation and effectively converts that into sugars eventually. So chlorophyll. Now chlorophyll is actually not a particularly sturdy molecule, so you need something to mop up bits of atoms and molecules called free radicals that might be in the leaf that would destroy the chlorophyll molecule. So also in the leaf you have carotenoids, which mop up these free radicals, as they're called. And so they're there to reduce damage in the leaf. Now, when the leaves die, the chlorophyll dies first, if you like. That's the first bit of chemistry that stops existing. And then the carotenoids just last a little bit longer because they can cope with the damage. And then when they disappear, when they die off, you're left with these other chemicals called anthocyanins, which are a lot of flowers are coloured with these particular chemicals as well, and they're affected by pH. So no, people are still arguing about why anthocyanins are in leaves. Maybe there's the reason they give for it. And indeed, these are the chemicals that live longer or survive longer within the leaf as it dies. So yeah, so colour there is giving an indication of the chemicals that are in there and the relative proportions. So what makes colour? Well, we've said it's to do with the spectrum, it's to do with the eye, and then also to do with the brain. And how do we see colour? Well, okay, time for an experiment. Are you ready? I'd like you to stare at the centre of the screen. At the centre, can you see a little rotating cross? Stare at that cross. Don't look left or right or up or down. Just keep staring at the cross. I want you to get kind of fixated on that cross, that rotating cross. That was the sound of me drinking some coffee. Right. Now I'm going to get rid of the elephant. Now keep staring at the screen. Is it still there? Can you still see it? It'll be there for a while and then it will disappear. What colour was it? Go on, let's do it again. So stare at the cross, keep staring. Oh, sorry. Keep staring, keep staring, keep staring. Don't look left or right or up or down or you'll blur the image. And what's happening is that different parts of your retina in the back of your eye, they sort of get fed up with seeing those colours, and so they switch off, they stop seeing those colours, and you become blind to that particular colour. And then when I show you nothing, you see the opposite of that colour. This is an after image. Maxwell, the scientist, used this to investigate colour blindness. Hey, let's do it with this one. So keep staring at the rotating centre of the rotating cross in the middle. I mean, you recognise the pattern, so you know where this is going, but we'll do it anyway. We'll do it for fun. Okay, keep staring, keep staring, keep staring. And whoa, does it work for you? It works for me. Yep. Oh wow, it's still there, and the colours are quite obvious. So, oops, okay. So the bit that was cyan turned into red, the bit that was yellow turned into blue, and the bit that was black turned into white, actually. So every color has this opposite color. Designers know about this, and they call them complementary colors, because they are as far apart from each other as possible, so they sort of go together well. Right, let's go back to this graph here, the response of the human eye to color. We can't see infrared, we can't see ultraviolet, and we have a peak response. So wait a minute, what's that? Can you see that on the left-hand side, there's a kind of double lump? I think there are some details being hidden in here, and it's true, there are. We don't have just one sensor to light in our eyes, we have three that are responsible for color vision. And there's one sensor that kind of gets more stimulated, more excited, gives a higher signal if there's blue light onto it, which is indicated by the blue line on the left-hand side. There's one that kind of gets excited more by the red end of the spectrum, that's the red line, and there's one that's kind of excited by stuff in the middle. So there's three signals. We kind of have a pixel system in our eyes, three signals giving us indications of how much red, green, and blue light there are in whatever it is that we can see. So it's just a sort of pixelated vision. And these three signals are what gives us the sensations of color. So for us, color is a three-dimensional thing. This is my boss, Julie, in the 1980s with her visual research colorimeter. And this worked by shining different amounts of red, green, and blue light into your eye. And then you had to adjust the proportions of these colors to match another color. And from that, we could work out how people saw color, their response to color. It was based on an experiment done in the 1920s. And this is what you will see if you look down that eyepiece. There's a kind of illuminated patch just to make sure that your eye is at daylight illumination conditions. Your eye changes its response with the amount of light that's present. And we wanted to see what it looked like at daylight levels. And then we took a spectrum and we just selected part of it. Let's say we take the cyan part, that bit there. And we're going to match that with some primary colors, which are these colors here, which again, we've taken from the spectrum. So in your mind, how much of each of those three colors do you think we will need to match that color on the upper part? What do you think? I'm using telepathy over the internet here. And I'm thinking that maybe some people think there'll be no red in there at all, and that you'll have 10 units, that the dials go up to 10. So maximum amounts of red and of blue and green. And that's what you would actually get. That is not a good match, is it? Nope. So let's tweak the dials. What do you think? No, no red. That red won't do anything. Okay, you're suggesting more blue. No, we can't have more blue because it's on 10, which is maximum. So let's have a little less green. That's too much less. There we go. Right. So that is our mix. 10 units of blue, 6 units of green, and no units of red. And that particular match, if you do the thing properly, is unique to you. And in fact, varies with different parts of your eye, etc., or which eye you're using. And we can specify exactly which of these primaries that we're using. They're not just randomly chosen. And from that, we can map out the performance, your response to color. So the results from the 1930s were put together. Okay, the late 1920s, 17 observers, 17 people, and they created this kind of response to light. Don't worry about the shape of that. All we really need to know is that we've got this beautiful color map, which is the proportion of redness against the proportion of greenness. And if it's not red and it's not green, it's blue. So it's at the bottom left-hand side. And you can create any color that you can see, you should be able to plot somewhere on this chart. Here we go, it's another picture of it. So redness against greenness. Now, if you had a third red, a third green, and a third blue, can you kind of look at the image? Can you see? That's a kind of neutral color. It's actually quite hard to see exactly where the neutral color is on this. If you had equal amounts of red and green, a half, yes, you get yellow. So that's good. That's the way that should work. And if you didn't have a lot of red and didn't have a lot of green, you'd have blue. So that seems to work too. There's something missing. That's lightness and darkness. So we're looking at a slice through three-dimensional color space. To do the job properly, you need another number that indicates how much light is present. So you have, it's as though we've taken a bit of ham and we've sliced through it at a particular lightness level. So if you like, coming out of the screen, there'd be lighter versions of these colors, and going into the screen, there'd be darker colors. So that's where you'd have your brown and your white and your bright yellow and so on. Now we can plot things on this chart, and there are British standards that describe exactly what the colors of traffic lights must be. So in the UK, you are only allowed to sell traffic lights if they are in these shapes, within these shapes, the colors are within these shapes. So you can see there's a very limited color range that red traffic lights have to be. Amber has to be in that sort of triangular shape, and the green has to be in that rather odd shape there. And when I first looked at traffic lights, I thought, that's not the greenest green you could ever have. It's sort of bluey green, isn't it? And there's a reason for this. You can also plot color blindness on this chart. And if we plot this particular type of color confusion, which people describe as color blindness, all the lines along that, each one of those black lines, for a person with a particular type of color blindness, if this chart was working properly, which is not, because it's just using colors on your screen, this is an indication, really. All of the colors along that line, along the black line, would appear to be the same hue. You wouldn't be able to discriminate. There might be different lightnesses, but they would kind of look the same sort of flavor, if you like, of hue, as we call it, of color. And can you see there are no lines connecting the red light with the green light? There are connecting the red and the amber. So people with this type of color vision would actually not be able to tell the difference between red and amber, but they certainly could tell the difference between red and green. And if you had a really bold green, like I thought you ought to have, you can see how the colors are actually, well, the lines are a bit closer. So you might start to confuse green with red. So that's why they have this distinctly bluey green with traffic lights. That's one of the types of color blindness. There are three types of color blindness because there are three types of sensor in the eye, and it doesn't work for all of them, but hey ho. 2 out of 3 ain't bad. This is how you would measure color. You have some white light or whatever colored light coming in, you bounce it off something. In the old days, you'd have used a prism. These days we use something that reflects and refracts light into a rainbow, called a diffraction grating. And then we can take an image, a photo of the spectrum that comes off, and that gives us an indication of what the light is made out of. Or you could just have 3 detectors. Here we've got some yellow light going into a kind of scattering device, and there's 3 sensors there, which I've labeled as being kind of reddish colored, greenish colored, and bluish colored. And those 3 numbers that come out of those are just like the way that the human eye works. There's an app on an iPhone, can't be bothered to show it to you now. It's called Color Talk. I don't know if Android people get it as well. It's really good fun. Download it, Color Talk, and it works just like this. And it goes further and actually changes. It talks out loud and says the colors that it's measuring, and it does exactly this. It measures the amount of green, red, and blue light in there, and reports numbers. So here's somebody measuring some creme brulee because they wanted to. But I have to tell you that perceived color is more than just amounts of red, green, and blue light. Here's my next fun demo. Are you ready? So you're going to stare at the cross, okay? But be aware of what else is going on around you, but just keep staring at the cross. Are you ready? I'm going to rotate a white thing that covers over these pink things as it goes around. Ready? Here we go. Keep staring at the cross. Now, I'm doing it at home as well. For me, I'm seeing a yellow thing going around. It's a bit like the elephant thing earlier on. In fact, it's that same elephant color, actually. And eventually, the yellow thing eats up all of the pink things. This is called the Pac-Man demo in some places. And it's all to do, again, with after images and the fact that the eye gets bored with seeing something. And it's weird. So let me tell you about the things that determine the way we see color. So somebody took some photographs of the back of a retina, and they kind of got a colored pen and colored in the different cells. They're called cone cells that are responsive to different parts of the spectrum. And you can see that the distribution varies. Certainly there are less blue sensitive cells than the others, that's normal. But the proportions of red and green do tend to vary as well between individuals. And that's controlled by the genetics. The genetics are what decide the responses of each of these things. They have actually done some genetic manipulation experiments where they've got colorblind animals to see color by changing the genetic coding within the retina. When I did my experiment measuring the shininess of cats, sorry to go on about that, but it is a great story, I came across this next thing, which is linearity. So if you, on here, this is the whitest white that your screen can display and the blackest black that your screen can display. Where do you think the 50% level, what do you think halfway between should be? Well, as far as your display system is concerned, it's that. But does that appear to be exactly halfway between the two? I don't think so. I think that's, is it too light? I think maybe it's too light. So we have a non-linear response to light. And this is because we have to accommodate such an enormous range in lighting levels, from starlight to really bright days. It's my daughter and my father going for a walk in the park, in the bluebell wood, actually. And my dad was 70, my daughter was about 1.5, I think. And do you remember what I was saying about the ultraviolet radiation coming in and being absorbed by the lens? Well, over time, that lens kind of gets damaged. It yellows with age. So my dad's, a lot of the yellow part of the spectrum is absorbed by his, sorry, a lot of the blue end of the spectrum is absorbed by his lens. Less blue light can get through. So on the left-hand side, I've changed the image slightly there. Left-hand side, he sees everything kind of a bit more sepia-ish toned, whereas my daughter would see things that are bluish, a lot brighter. So the way we see colours varies with our age until we have the cataract operation. And with light level as well. So this is that same bluebell wood as you would see it during the day, but at night levels, well, this other set of detectors comes into play, the rods. We have a whole separate vision system that allows us to see light at night levels. The rods start to contribute a lot more and the cones a lot less because there's not really enough light to excite them. So during dawn and dusk, the bluebell wood will look a bit more like this. You'll lose a lot of the sensation of colour, but the bluish part of the spectrum excites the rods more, so they appear a lot brighter. So that was it during day, and that was it at night. So you can do this experiment yourself next time you go into a bluebell wood. Have you ever done decorating? The colours never turn out like they're supposed to, do they? Never, 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 never. And I'm now going to explain why. It's to do with field size. So the swatch that you look at, the little patch of colour in the store, isn't the same size as your building, is it, or the walls? And so when you look at larger areas, you see light differently, you see colour differently to when you look at small areas. And this is why. Sorry, rather complicated picture, but well, this is what we've got. So in the center of the eye, there's a lot more cones. Can you see the green curve? Load more curves, load more sensors. So your color vision is really quite acute in those parts. But as you move further out, these rods, which are on during the day, and contribute towards the luminance signal, but don't tell you anything about color. There are more of them as you get further away from your center of vision, if you like. And so you're kind of color, not so color responsive further out. So larger areas will sort of have less color in them than smaller areas. So your color vision really does change with the area that you're looking at. And I thought I'd do this, and people can pick this apart. I just wanted to illustrate how amazing our color vision system is, because this is the scene as the light enters our eyes. And that's very pretty, isn't it? But actually, I don't know if you know, the eye is a bit like a pinhole camera. So the first thing that the brain does is turn the thing upside down so that we see the world the right way up. And then, of course, I've got a scale here. These are every 10 degrees. So the full width of your whole field of vision is everything in the coloured image here. And you've got a blind spot. Now, it does not appear as a black dot here. I mean, literally, you just don't see that anything's there. So everything that's around it kind of pinches in together. I couldn't work out how to do the design to show that, but everything kind of pinches in, and we're just not aware of anything that's happening in that area of vision. Why is that there? Because the cabling that carries the signals from your cells in your retina are actually lying over the top of the retina, and they all kind of go in at one point. This is the fiber optic, not fiber optics, the optic nerve, okay, which contains all of these bundles. And there are no, as they leave the eye, there's not enough space really to put these color sensitive cells there. So you're just not sensitive to light there at all. And this tiny little ring in the middle, that's where you are most sensitive. That's where, to color, that's where most of the color sensors are. So actually, your response to light is probably a bit more like that. Your response to color is a bit more like that. Although obviously the brain does a fair bit of working out and assumes that things don't change color depending on whether you're looking directly at them. But there's some very clever sort of software going on in the brain to give you the full thing. And then finally, I wear varifocals. And so the bottom of my image is in a different focus to the other. And yet I'm not aware of that. The brain works that bit out. So how you get from that to the real image is really quite amazing. This is Teresa, who works at MPL, and she's got this big sphere that we put light bulbs in. And it's great because you walk actually inside it. She was measuring how bright the light sources are. And it's a great thing to go inside because there's no ceiling or floor or wall. It's just and the acoustics are weird as well. It's quite an experience. But for fun and open days, we put green lights inside there, and people go in and they just enjoy the acoustics and the experience, and then they come out. And because their eyes have got so accustomed to the green light and bored and fed up with seeing it, when they come out, everything looks pink. It's a kind of variation on the elephant thing that we showed earlier. And then we've got this odd thing called color constancy. These are all things that showing you that it's more than just amounts of red, green, and blue light. So can you see there that the grapes are this greeny grape color? And there's your picture with lots of other things in there as well. Let's use the same picture again, but change the general cast of it, the general hue. And can you see now that this line here is orange? It's not grape color at all. And yeah, well, oranges are orange. What came first, the fruit or the name of the color? I don't know. And there's that orange there. Now, the freaky thing is that actually those two colors are exactly the same. But even these, if you look at these two, the swatches kind of look different, don't they? And that's because we refer everything in the image to the whitest thing that we can see. And we assume that colors are constant within any given sort of setup. So we're referring everything really to the white that's here, which is obviously a bluey white here and a pinky or reddish white here. So this is greener than that, so it appears green. And this is oranger than that, so it appears orange. But it is weird that in an absolute way, these colors are actually identical. And if I would say what color's a banana, you'd say it's yellow, they're yellow. And there's some great papers out there talking about just expecting things to be a particular color, and therefore they inform the way that you see them. So I made this, it was such a good demo that someone nicked it. But this bit here, we've got two rows of pink, and they are actually identical pieces of pink material, paper. You can make one of these at home. But depending what they're next to, you see them as doing different colors. Now, I'm staring at the screen at home now, and to me, if I stare at it for long enough, I can start to convince myself that they are the same color. But if I look away and then look back again, oh, they've changed. And if I move back, if I put my head quite far back, now they appear to be different again. So it's one of these things that if you stare at, it actually changes. So it changes with time. And this is to do with the fact that colors are affected by what is around them. Oh, and the field size as well, which goes back to that, how we see things in different sizes. Gosh, look at those. Those really are very different now. Again, until you stare at them for quite a while, and then they start maybe to appear the same. Depends on the size of your screen. If we were doing this in a theatre, different people in different parts of the auditorium would get different sensations of this, and so would report different degrees of amazedness. People at the front, not quite so amazed as people at the back. Artists know about all this kind of stuff. So here's Van Gogh with these yellow stars in blue skies, so that the blue looks bluer and the yellow looks yellower. And he's also got some orange versus some green going on down there. And this is Peter Jones's colorscape. Now it looks like an inflatable giant castle from the air. This is the air, from the air. And these little tiny dots here are people. I mean, it's quite a large thing. And you wander around inside the giant inflatable between these different cells, and the light just from daylight makes them appear the color that they are. And because the light, you are within the light source effectively, the colors are really, really bright. You almost eye-dazzlingly so. And so I have never seen such a bright green next to such a bright red. And this photo will not do it justice. Even on a cloudy day, the effect is quite stunning. So if you hear that this colorscape, it tours around the place now and then. Oh, it won't be at the moment, will it? But when we're back to normal, check this out. Go and find out where it's tethered. There are several of them touring around, and it really is worth a visit. So how do we see color? Well, I'll just do a quick review. Spectra, which we, in our eyes, squash down into 3 bits of information: redness, greenness, and blueness. Your psychology, and also the context, what is around it, and how the cast of things, the orange versus the grape. The psychology of the stuff as well, my goodness. Yeah, sorry, that says physiology up there, doesn't it, the first one? So physiology, which is to do with the way that the eye and the retina works, and the electronics in there. And then the memory as well, the banana aspect. So we're nearly finished. Ah, it's been such fun. This is my favorite demo, nearly. Can you see the areas labeled A and B? It's Adelson. Google Adelson checker chart when you're finished, and print this thing out. It works just as well. So look at this thing. The area labeled A and the area labeled B, do they appear the same or different to you? Well, I would say they appear different to me. I think B looks quite light and A looks quite dark, but they are actually identical. Look, that area there, the B area, is the same as this big block now, but the big block is also next to A, and they appear the same as well. So A and B are actually identical in color. And if I got that app, Colorsay, C-O-L-O-R-S-A-Y, Colorsay, and I measured the screen in those 2 areas, A and B, I'd get the same result because they are actually absolutely the same color. So this is all the psychology stuff and a bit of physiology mucking up our response. And what's actually happening, there are 3 things going on here. One is that this appears to be in shadow, B appears to be in shadow, and our brain programs us to see things that are in shadow as being darker than they really are. A is not in shadow, so it appears to be, well, what it is. B is surrounded by dark things, and so that's like the checker thing that we saw before. The darker things are affecting and making the B look lighter, and the light things around A make A look darker. And finally, and this is the 3rd effect, and this is the weirdest, and this is the one that scares me most, is that we recognize the pattern. And we know that all the light things are where they should be, and all the dark things are where they should be. And we know, because we recognize the pattern, that A is a dark thing and B is a light thing. So what we think we're seeing is actually telling us what we're seeing. That's mind control. That's awful. That's terrible. Oh, I hate it. If you print it out, print this thing out, you can actually fold it and have A and B right next to each other, and you can see that they are identical. The ink density is identical. And then when you unfold it, they will appear different. It's just weird. It's not magic, it's science. Right, back to this. There's the conference. There was a conference. There was a conference on this dress, and everybody talked about all their different pet areas of study. So I think almost in summary, yeah, we are at that point now. There are loads and loads of different ways that we can see colour that inform the way that we perceive colour, and that mucked up people's perceptions of a single image. And I think that's amazing, and I think we should celebrate that. It's nice that the world is weird. This is my last image. This really is my last image, honest. So can you see that there's a green rings there and red rings? Let's enlarge that so you can see it a little bit clearer. Oh, can you see that they really are green? Because when they're next to that green blob, they're green, right? Which is what we expected. Good. Now I'm going to do the same thing with this one. There you go. The green is green and the red is red and the blue is blue. And let's just shrink it back down again. But hang on a minute. Now I'm going to move my head a little bit further away. The further away you look at this, the better. Do they all look the same? Does the top bit, does the green still look green? No, not for me. And again, if we were doing this in the theatre, the people in the back seat would get the best version of this. The upper one, I think if you're at the other side of the room, you're going to see like that. And again, if you're at the other side of the room, you might see that. So under the right circumstances, you'd see those three colours as being identical, if that makes sense. It gets worse. Here's another image, and I'm going to draw your attention to that being identical. And I tried to get the eye about the same colour as well, but I think it's maybe a bit dark. Again, it will vary on your age, the area being viewed, whereabouts you are, whether you use your left eye or your right eye. But can you see where this is going? Because those two eyes are actually identical. And it's just because the left eye, well, the one that we're seeing on the left, is surrounded by this pinky colour, that makes it appear bluer than it really is. So those two are really the same. It's weird, isn't it? So I have just proved that you have seen those colours identical, and that's where we started, and that is where I am going to end.
And thank you very much, Andrew. Really, really good. Really fascinating. And I think, you know, to cram so many experiments and kind of demonstrations in was really fascinating. And they all worked really well. I could get them all to work here as you were talking on the screen. So really enjoyed that. So we have got some people obviously watching on Facebook, and they're just sort of catching up because there's a slight delay on that, and also on Zoom. While you were talking, there was a question, and it was from Alan, but I think oddly enough, you answered the question about 5 minutes afterwards, which was to do with, he was asking about when you see things at night and the colors are less noticeable, and is it something to do with the eye or the illumination? So I think you kind of answered the question, but you might want to just sort of summarize there. It's to do with the cones and so on, isn't it?
Yeah. So we've got the cones, which are cone-shaped cells that work during the day and give us the sensations of color. And they're kind of sensitive to a third of the spectrum, broadly speaking, yeah? Now, at night, you've got much more sensitive cells that are kind of, in a way, almost dazzled by day, called the rods. But actually, they do work during the day as well. But they give us more information for peripheral vision, particularly if, if someone's coming at you from the side with an axe. So they are really, really useful. And that's the reason, and the cones are concentrated more towards the center of the field of vision and the rods further out. And that's why the color perception changes with field of view. So they are kind of all on and working during the day, but at night there just isn't enough light to excite the cones. The cones, which is why you kind of become blind in the center of your field of vision at night. And astronomers, if they're looking up, well, anybody looking up at the stars, you don't look directly at the star. You look slightly to the side of it because you've got this kind of blind spot, because the stars can only really be seen by the rods.
Yeah.
What we call the night vision system and the day vision system.
Yeah, and so people can try that if they've not sort of come across that themselves already. I mean, and the other thing that I thought was interesting, and you touched on it at the beginning, actually, is that actually, although the science of color is really interesting, it's actually really big business, isn't it? Getting the colors right.
Yes. Apple's phones, the sales are flagging. Let's add some more colors. And then suddenly the numbers go up. And psychology can be used to manipulate. I mean, I'm not going to say whether things are right or wrong, but British Petroleum, the colors of their signs, their logos and everything changed from motor racing green to a kind of optimistic future green and yellow. And psychologists are employed to choose the colors of things. And if you're an organization, you can contact a psychologist and you can say, I would like, these are the values of my organization. And so they can then tell you which colors then map to those values. You know, do you want to be reliable? Do you want to be risk-taking? These are kind of mapped onto different colors that you can then incorporate into your logo. So it's not just about the shape of the logo, but the colors that are used in there.
Mm. And before you started the talk, I sort of thought, well, color is all mainly physics, yes. And because you were coming from the National Physical Laboratory, that seemed to be very sensible. But as you were talking, it obviously became clear, of course, chemistry and dyes and so on is very important, but actually it's incredidly multidisciplined, isn't it?
It is,
as you've shown,
there's
biology as well.
Biology, huge amount of psychology. Yeah, a physicist might be required to get machines to measure things the way that people see it. But the way it actually works goes way, way beyond just signals and numbers. And the biological systems are webs, aren't they? And everything is influenced by other things, and it's all very, very complicated. And we have to admit that the perception of color is a biological thing. The psychology is built into it. And personality, and different cultures have different feelings about different colors. Some parts of the world view green as in a completely different way because you look outside and you don't see green, and you don't have so many green trees. And there are color preferences. You used to have one type of photographic film in Japan and one type in America, Kodak versus Fuji. And the way that these different films rendered colors were different based on what those different populations culturally preferred to see. So the Americans like to see lovely greeny yellow grass, whereas the Japanese like to see bluey greeny grass. And so the response of the films gave you these different casts of color. And in a photograph, do you want color preference or do you want color fidelity? And I've got friends who just, when they take a photograph, they immediately put the whole thing through a filter so everything looks rosier, more colourful and more vibrant, because that's the image you're going to post on Facebook, not the washed out reality.
Yes, that's what the Instagram filters made.
Yes.
Instagram so popular was the ability to manipulate like that. Yeah, and obviously, I mean, it's a shame that Gina had to drop off because, there is synergy between her talk on the brain and your talk on color, and that was not by accident, is that the fact that there's an awful lot about how the brain interprets the color, which you've demonstrated so well today. Yes. And it would have been nice to have had Gina just to answer a couple of questions as well, actually, about any of the neuroscience research that she's aware of in color. So that'll have to wait for another day. But clearly, for people that are watching that are interested, as it's a family show, perhaps studying color and making it part of their career in the future, children that are at school at the moment, it's clear from what you've said that actually people doing biology, people doing physics, people doing chemistry, people doing or having an interest in psychology can all...
And design, branding.
Exactly.
I'm part of something called the Colour Group of Great Britain, and we are an interest group. It used to be part of the Institute of Physics, but there were so many non-physicists getting involved in it, artists and whatever. They just became a charity in their own right. So again, check that out, the Colour Group of Great Britain. We celebrate all aspects of colour, all of these different things, the psychology, the design, the art, just the history of colour as well. I mean, how pigments in paintings have changed over time might comes into it as well. The subject's enormous. Yeah,
I mean, the science of looking at art and tracing from the dye pigments, the type of art and whether it's genuine art or not, that's a whole forensic subject.
I mean,
in itself,
how long do these things continue to represent the colour as the artists intended them to be? Blue might have become white with age, and then art historians will say, in this image white represents, but it was blue originally.
Yeah, really, really good. Well, thank you ever so much, Andrew. That was a fantastic end to this year's festival, bringing together a whole range of different concepts and science, which is really fitting in. So thank you for joining us. I know you've actually got yet another thing to go on to later this afternoon. So you're busy Saturday for you. It's much appreciated you could
It's an absolute
dial into
pleasure.
Malvern.
Hope to be there in real life next time.
Yes, no, we'd love to have you. So thank you very much. Just remains me to say thank you to everybody who has watched the festival, both today and earlier in the week, and also to all our speakers, our sponsors and our supporters. So we will hopefully see everybody next year. And of course, we hope next year it'll all be in person and back to the sort of things that we're used to. And I have been joking with people that next year it will be the Malvern Festival of Inoculation as opposed to innovation. So we can but hope. When I press end, everybody drops off. So thank you very much. See you again next year and take care.